In this section, we will study about the phase diagrams and transformations related to iron-carbon systems. Let us now study about the iron-carbon phase diagram. The iron-carbon phase diagram is one of the most important diagrams of any metallic system. Here, in this figure, we can see the iron-carbon phase diagram, where the y-axis is represented by the temperature scale, while the x-axis is represented by the increasing composition or weight percent of carbon. Now, the vertical axis in the left hand side denotes the zero weight percent of carbon, that is pure iron, while the vertical axis in the right hand side denotes a particular phase called cementite, which is actually a chemical compound of Fe3C having the carbon weight percent of 6.7. Therefore, as a matter of fact, the iron-carbon phase diagram should be called the iron Fe3C, that is cementite, metastable diagram, since in real practice the nucleation of stable equilibrium graphite, that is pure carbon, is very much difficult. Let us now talk about the different phases present in the iron-carbon phase diagram. In the previous section, we have studied about the cooling curve of pure iron showing polymorphism or different crystal structures. Now, when carbon forms the interstitial solid solution with the different forms of pure iron, we get the different phases at different temperature ranges in the iron-carbon phase diagram. For example, in the cooling curve of pure iron, below 910 degrees centigrade, we get the alpha iron showing BCC crystal structure. So, when carbon forms the interstitial solid solution with alpha iron, we get the ferrite phase in the iron-carbon phase diagram. Similarly, below 1400 degrees centigrade, in the cooling curve of pure iron, we get the gamma iron having FCC crystal structure. When carbon forms the interstitial solid solution with gamma iron, we get the austenite phase in the iron-carbon phase diagram. Similarly, above 1400 degrees centigrade up to 1540 degrees centigrade, that is the melting point of pure iron, we get the delta iron having BCC crystal structure. So, when carbon forms the interstitial solid solution with the delta iron, we get the delta phase in the iron-carbon phase diagram. Thus, as and when the carbon forms the interstitial solid solution with the different forms of pure iron, we get the different phases at different temperature ranges in the iron-carbon phase diagram. And since the vertical axis in the iron-carbon phase diagram represents the pure iron, over here we get the same temperature ranges for different phases, that is 912 degrees centigrade, 1400 degrees centigrade and 1538 degrees centigrade, similar to the temperature ranges in the cooling curve of pure iron. To come with the next phases, in between the ferrite phase and the cementite phase, we get the combination of ferrite and cementite, which is actually the layers of ferrite and cementite termed as pearlite phase. Here we get the uniform liquid phase. In between the austenite and liquid phase, we get the austenite plus liquid phase, and in between the austenite and cementite phase, we get the austenite plus cementite phase. So these are the different phases which are present in the iron carbon phase diagram. Next, we talk about the steel and the cast iron. The iron carbon phase diagram may be divided into two portions, the left hand side pertaining to steels, while the right hand side belongs to cast iron. It is obvious that melting point of cast iron is far lower temperature than that of steels. Now, below approximately 1.8 weight% of carbon, we call it as steel, while with higher than 1.8 weight% of carbon, we call it as cast iron. Now, with the increasing weight% of carbon, the steel becomes brittle or the ductility decreases. That is why the cast iron is much more brittle compared to the steel, because the cast iron has the higher percentage of carbon compared to steels. Moreover, here the cementite phase or Fe3C is itself a brittle phase. Let us now talk about the few relevant points and temperatures in iron carbon phase diagram. Firstly, the maximum solubility of carbon in the ferrite or alpha iron is 0.022%, which is denoted by this point, while the maximum solubility of carbon in the austenite or gamma iron is about 2%. Over here we get the eutectic point having the eutectic composition of 4.3 weight% and eutectic temperature of 1147 degree centigrade. Over here the liquid phase on cooling get transformed into two solid phases of austenite plus cementite. Next, here we get the eutectoid point having the eutectoid composition of 0.76 or 0.77% of carbon and the eutectoid temperature of 727 degree centigrade. So over here the austenite phase on cooling get transformed into the two solid phases of ferrite plus cementite. In other words, the austenite transforms into an eutectoid mixture of ferrite plus cementite known as pearlite. Steels with carbon less than the eutectoid composition, that is in the left hand side of this eutectoid point, is known as hypoeutectoid steels, and those greater than the eutectoid composition, that is in the right hand side of the eutectoid point, is known as hypereutectoid steels. In hypoeutectoid steels, we have primarily ferrite plus pearlite phase at room temperature, whereas for the hypereutectoid steels, they are cementite and pearlite. Now, the cementite is noticed over here as a network around the pearlite colonies. Since cementite is a hard and brittle compound, so the hypereutectoid steels have lower ductilities. So, since in the hypereutectoid steel have the composition of pearlite plus cementite, and for the hypoeutectoid steel the composition is pearlite plus ferrite, and cementite is a brittle phase compared to the ferrite phase. So the hyper-eutectoid steel is a brittle one compared to the hypo-eutectoid steel. So these are the different relevant and significant features of the iron-carbon phase diagram. As mentioned in the previous section, the iron-carbon phase diagram illustrates three types of phase reactions. The first one is a eutectic reaction at composition of 4.3 weight% of carbon and eutectic temperature of 1147 degree centigrade, where the liquid phase on cooling get transformed into two solid phases of austenite plus cementite. The second phase reaction is a eutectoid reaction at composition of 0.76 or 0.77 weight% of carbon and eutectoid temperature of 727 degree centigrade, where the austenite phase of eutectoid composition 0.76 weight% of carbon on cooling get transformed into two solid phases of ferrite plus cementite. Now, after the eutectoid reaction, by means of lever rule, we get the compositions of alpha as 0.022 weight% of carbon and the composition of cementite to be 6.7 weight% of carbon. So we get separate compositions of ferrite and cementite phases by means of lever rule. The third phase reaction is a peritectic reaction at 1493 degree centigrade, where from the liquid plus delta phase on cooling we get the single solid phase of austenite. So these are the few significant phase reactions which are revealed in an iron-carbon phase diagram. The figures over here reveal the variations in mechanical properties with respect to the carbon content in case of plain carbon steels having microstructures consisting of fine pearlite phase. In the first figure, we can see the variations in yield and tensile strength as well as the Brinell hardness with respect to the carbon concentration, where we can see that strength and hardness increase with increase in carbon content. In the second figure, we can see the variations in ductility in terms of percentage elongation and percentage reduction in area, as well as the Izod impact energy with respect to the carbon concentration, where we can see that opposite to the trend in strength and hardness, ductility and toughness decrease with increase in carbon content. So this is about the variation in mechanical properties with respect to the carbon content in a steel. We will now discuss about the development of microstructure in iron-carbon system. Let us first consider about the eutectoid steel. In this figure, we can see the bottom left corner of the iron-carbon phase diagram, where we can see the uniform phase of austenite or gamma, the ferrite or the alpha phase. Here we can see a combination of ferrite plus austenite, and over here a combination of ferrite plus cementite, togetherly termed as pearlite. Now considering, for example, an alloy of eutectoid composition, that is 0.76 weight percent of carbon, as it is cooled from a temperature within the gamma phase region, say for example at 800 degree centigrade, that is beginning at this point A as shown in this figure, and moving down the vertical line x dash, which actually represents the particular alloy composition. Now initially at point A, the alloy is composed entirely of the austenite phase, having a composition of 0.76 weight percent of carbon. So since we are standing in the austenite phase, we get the microstructure at point A in this particular inset, where we can see the uniform austenitic grains. Now from point A, as the alloy is cooled, there will occur no change until the eutectoid temperature, that is 727 degree centigrade, is reached. So upon crossing this particular temperature to point B as shown in this figure, the austenite transforms according to this particular equation, which represents the eutectoid reaction, that is the austenite phase with composition 0.76 weight percent of carbon on cooling get transformed into the ferrite or alpha phase having composition of 0.022 weight percent of carbon, and Fe3C or cementite phase having composition of 6.7 weight percent of carbon. Now the microstructure of this eutectoid steel that is slowly cooled through the eutectoid temperature consists of alternating layers or lamella of the two phases, that is ferrite and cementite, that forms simultaneously during the transformation as shown in the reaction. Now in this case, the relative layered thickness is approximately 8:1. Now over here, the microstructure at point B is represented by this particular photomicrograph as shown in this figure. Here we can see the photomicrograph of a eutectoid steel showing the pearlite microstructure consisting of alternating layers of ferrite, which are actually the thick light phase, and the cementite or Fe3C, which are the thin layers, most of which appear dark. Now the pearlite exists as grains, often termed as colonies. Within each colony, the layers are oriented in essentially the same directions as shown in this figure, and this orientation varies from one colony to the other. The thick light layers are the ferrite phase, and the cementite phase appears as thin lamella, most of which appear dark. Now many cementite layers are so thin that adjacent phase boundaries are indistinguishable, which layers appear dark at this magnification. Now mechanically, the perlite has the properties intermediate between the soft ductile ferrite and the hard and brittle cementite. The alternating ferrite and cementite layers in perlite form because the composition of the present phase, in this case the parent austenite phase, having composition of 0.76 weight% of carbon, the composition of this parent phase is different than either of the product phases. In this case, the ferrite having a composition of 0.022 weight% of carbon and cementite having a composition of 6.7 weight% of carbon, and the phase transformation requires that there be a redistribution of the carbon by the process of diffusion. Furthermore, after point B, subsequent cooling of the perlite will produce relatively insignificant microstructural changes. So, this explains the development of microstructure in case of eutectoid steel while cooling from the uniform austenitic phase. Let us now talk about the diffusion process accompanying the eutectoid transformation. We have already discussed that the alternating ferrite and cementite layers in the perlite form because the composition of the parent phase, in this case which is austenite, having composition 0.76 weight% of carbon, is different than either of the product phases, that is ferrite having composition of 0.022 weight% of carbon and cementite having 6.7 weight% of carbon. Therefore, such phase transformation actually requires that there is a redistribution of the carbon by the diffusion process. Now here, this particular figure illustrates schematically the microstructural changes that accompany this eutectoid reaction. Here we can see that the orange layers indicate ferrite or the alpha phase, while the blue layers represent the cementite phase. Togetherly, the layers of ferrite and cementite form the perlite phase, whereas this is the austenite grain boundary, and as the perlite phase is growing in size towards the austenite phase, we get this growth direction of perlite. Over here, the directions of carbon diffusion are indicated by arrows. Now carbon atoms diffuse away from the 0.022 weight% of ferrite regions and into the 6.7 weight% of cementite layers, as the pearlite layer extends from the grain boundary into the unreacted austenitic grain. As we can see that due to the carbon diffusion from the ferrite to cementite phase, as this pearlite phase is growing in size, it is growing towards the unreacted austenitic phase to cover up the same, and we get this growth direction of pearlite. Now the layered pearlite forms because the carbon atoms over here need diffuse only minimal distances with the formation of this particular structure. So this explains the diffusion process accompanying to the eutectoid transformation. Next we study about the hypoeutectoid steel. Here in this figure we can see the schematic representation of the microstructures for an iron carbon alloy of hypoeutectoid composition, which is represented by the dashed line in this figure, that is C0, containing less than 0.76 weight percent of carbon, that is the eutectoid composition as indicated by point O in this figure, as it is cooled from within the austenite phase region, that is point C, to below the eutectoid temperature, that is 727 degrees centigrade, indicated by TE. So in this iron carbon phase diagram, this dashed line represents the particular hypoeutectoid steel composition of C0. Here we get the uniform ferrite or alpha phase. Here the uniform phase of austenite or gamma. Over here the phase of alpha plus gamma, and here a combination of alpha plus cementite, togetherly termed as pearlite. So we are cooling down this hypoeutectoid steel from point C. At point C we are in the uniform austenite or gamma phase. So we can see the microstructure in this particular inset, where we can see the uniform austenitic grains. While cooling down further, we reach from point C to point D, where we enter into the phase of alpha plus gamma. Therefore, we get the microstructure in this particular inset, where we can see that the ferrite phase has started to nucleate along the grain boundaries of austenite. While cooling down further, we reach from point D to point E, where we can see in the microstructure that the ferrite phase has grown in size along the grain boundaries of austenite. So the amount of ferrite phase has increased within the grain boundaries of austenite. Now within this phase of alpha plus gamma, the amounts of these two phases, that is alpha and gamma, as well as the individual compositions of these two phases, are determined by lever rule. Now while still cooling further, we cross the eutectoid temperature of 727 degrees centigrade and we reach point F, where we can see the microstructure in this particular inset. Now while crossing this eutectoid temperature, what happens is that just before crossing the eutectoid temperature, the austenite which was remained in the microstructure having the composition of eutectoid composition, and while crossing the eutectoid temperature will immediately undergo the eutectoid reaction, That is, this austenite will transform into pearlite. So, in this microstructure, we can see the pearlite phase, which consists of the lamellar layers of ferrite and cementite. So, we can see over here the eutectoid alpha, that is the alpha which is formed due to the eutectoid reaction. Over here we can also see the pro-eutectoid alpha, which was already present before the eutectoid reaction, which we can also see in this particular microstructure at point E before crossing the eutectoid temperature. So, this happens to be the final microstructure of the hypoeutectoid steel, that is the pearlite having the lamellar layers of ferrite and cementite and the pro-eutectoid alpha. Now after point F, while cooling down further, the amounts of these two phases of alpha and cementite will vary somewhat as per the lever rule, but the microstructure will remain the same. So, this explains the development of microstructure for hypoeutectoid steel composition. Here, in this photomicrograph, we get to see the final microstructure for hypoeutectoid steel. Here, the darker regions are pearlite, which are the lamellar layers of ferrite plus cementite. Over here, the ferrite is the eutectoid ferrite that is formed due to the eutectoid reaction, while the lighter layers are the pro-eutectoid ferrite, that is the ferrite or alpha phase that has been formed before the eutectoid reaction. So, this is the final microstructure of a hypoeutectoid steel. Lastly, we come to study about the hypereutectoid steel. Over here, we can see the schematic representation of the microstructures for an iron carbon alloy of hypereutectoid composition, that is C1, as represented by this dashed line containing between 0.76 and 2.14 weight% of carbon, as it is cooled from within the austenite phase region, that is point G, to below the eutectoid temperature, that is 727 degrees centigrade. So once again, in this iron carbon phase diagram, this dashed line represents the hypereutectoid steel, in this case of composition C1. Over here, we can see the uniform phase of austenite or gamma. Here, a combination of austenite plus cementite, and over here, a combination of ferrite or alpha plus cementite, togetherly termed as pearlite. Now, we are cooling down this hypereutectoid steel from point G. At point G, we are standing at the uniform phase of austenite or gamma. So, we can see the microstructure in this particular inset, where we can see the uniform austenitic grains. While cooling down further, we reach from point G to point H, where we enter into the phase of austenite plus cementite. So, we can see the microstructure over here, that the cementite phase has started to nucleate along the grain boundaries of austenite. Now, within this phase of austenite plus cementite, the amounts of these two phases as well as the individual compositions of these two phases are given by the lever rule. Now, While cooling down further, after crossing the eutectoid temperature, that is 727 degrees centigrade, we reach point I, where we enter into the phase of ferrite plus cementite. So over here we can see the final microstructure in this particular inset. Now, during crossing the eutectoid temperature, what happens is that just before crossing the eutectoid temperature, the austenite phase, which was remained in the microstructure, having composition of eutectoid composition, and while crossing the eutectoid temperature, will undergo eutectoid reaction and will immediately transform into the pearlite phase. So over here we can see the pearlite phase, which consists of the lamellar layers of ferrite and cementite. Here within the pearlite we can see the eutectoid cementite, that is the cementite which is formed due to the eutectoid reaction. Additionally, we can find the pro-eutectoid cementite, that is the cementite which was already present before the eutectoid reaction, and that can also be seen in the microstructures before crossing the eutectoid temperature. Thus, this happens to be the final microstructure of the hyper-eutectoid steel, that is the pearlite phase having the lamellar layers of ferrite and cementite along with the pro-eutectoid cementite. Now, after point I, while cooling down further, the amounts of these two phases of ferrite and cementite may vary somewhat as per the lever rule, but the final microstructure will remain the same. So, this explains the development of microstructure in case of hyper-eutectoid steel composition. Here the photomicrograph represents the final microstructure of the hyper-eutectoid steel having composition of 1.4 weight% of carbon. Here we can see the darker regions represent the pearlite colonies, which are the lamellar layers of ferrite and cementite. Here the cementite is the eutectoid cementite, that is the cementite which is formed due to the eutectoid reaction. And here the lighter or the white regions represent the pro-eutectoid cementite network surrounding the pearlite colonies. So, this is the final microstructure for a hyper-eutectoid steel.